question is, using the property of determinant, prove that the determinant x square yz, y square zx, z square xy is equal to x minus y minus z minus x into xy plus yz plus zx. Now to solve this question, first of all I take the left hand side, which is given to me as x square yz, y square zx and z square xy. Okay, so to make this determinant into a very simple form, I apply a little bit of trick, and the trick is that first of all I'm going to multiply and divide this determinant with x, y, z. So in all I've done nothing. Multiplying and dividing by same thing to a determinant means that the value of the determinant is not going to change. Okay, after this what I'm going to do, I'm going to multiply x in the first row, y in the second row and z in the third row. Okay, so I'm going to obtain, on multiplying x in the first row, x square, x cube, x, y, z. Similarly, multiplying y in the second row, I'm going to obtain y square, y cube, y zx, which is equal to x, y, z, and z cube, x, y, z. Okay, here it is written zxy, which is equal to x, y, z. Okay, so after this what I'm going to do, I'm going to take x, y, z common from the third column. So on taking x, y, z common from the third column, I'm going to get x, y, z upon x, y, z, and these two are going to cancel out, and here it would be obtained 1 1 1. That is, in the column 3 I'm going to get all the three elements as equal to 1. So this makes my determinant converted into an easy form, because now I can make the two elements of the column 3 as equal to 0 by applying this property, that is R2 is changed to R2 minus R1 and R3 is changed to R3 minus R1. Okay, so applying this property, I'm going to obtain this as equal to x square x cube 1, the first row as it is. Second row will be x is y square minus x square, y cube minus x cube, and 1 minus 1. Similarly, z square minus x square, z cube minus x cube, and 1 minus 1. Okay. After this, I'm going to factorize these terms, y square minus x square, y cube minus x cube, and all these terms. Okay, so I'm going to obtain this as x square, x cube 1. The factors of y square minus x square will be y minus x into y plus x. Z square minus x square factors will be z minus x into z plus x. Y cube minus x cube will be written as y minus x into y square plus x square plus yx, and z cube minus x cube can be written as z minus x into z square plus x square plus zx, and 1 minus 1 will be 0. Right? Now I can see here that y minus x can be taken common from the second row and z minus x can be taken common from the third row. Okay, so taking y minus x, z minus x common from the second and the third row, I'm going to obtain this as equal to y minus x into z minus x. Okay, and the determinant remains as x square x cube 1, y plus x, z plus x, y square x square xy, z square x square zx, and here 0 0. Now to solve further, what I'm going to do, I'm going to apply this property, R3 is changed to R3 minus R2. Okay, so this is done because we have to prove that the determinant which was given is equal to x minus y, y minus z, z minus x. So if I subtract the elements of the second row from the elements of the third row, that is, if I'm going to apply this property, R3 is changed to R3 minus R2, I can get the third term, that is z y minus z or z minus y, common from the third row. right? So applying this property, I'm going to obtain this as x square x cube 1, the second row as it is, and the third row is going to change to z minus y. X are going to cancel out, x square are going to cancel out, so I'm going to obtain z square minus y square plus zx minus xy, and these two terms as it is. Okay, now taking the determinant further, this term can be factorized. So I'm going to factorize this term by taking the term z square minus y square plus zx minus yx. Now z square minus y square can be written as z plus y into z minus y, and from zx, yz, yx I can take x common, so I'm going to get this as z minus y. Further, taking z minus y common, I'm going to get this as z minus y into x plus y plus z. So I've arranged the terms also, so I'm going to get this as z minus y into x plus y plus z. So replacing this expression with z minus y into x plus y plus z, I'm going to obtain the value like this: y minus z into z minus x. These two terms remains as it is. Actually, whole determinant is going to remain as it is, but this term is going to change by z minus y into x plus y plus z. Now further, I can take z minus y as common from the third row. So taking z minus y from R3, I'm going to obtain this as z minus y, y minus x, z minus x, x square x cube 1, y plus x, y square plus x square, yx 0, and 1, x plus y plus z, and 0. Okay, now next thing what is to be done is to expand the determinant. Expanding the determinant along the column 3, I'm going to obtain these three terms as it is. So the expansion of the determinant would be 1 into the determinant obtained by removing the first row and first column, that is y plus x, y square x square, yz, 1, x plus y plus z, plus 0, because we don't have to worry about what is going to multiply here, because 0 into any value is 0. Further, on solving this determinant, I am going to obtain these terms as it is, and y plus x into x plus y plus z minus 1 into y square plus x square plus yx, that is minus y square minus x square minus yx. Okay, so multiplying these terms, multiplying these two brackets, I'm going to obtain this as y into x, yx, y into y, y square, y into z, yz, x into x, x square, x into y, xy, x into z, xz, right? Now you can see here x square and x square are going to cancel out, y square and y square are going to cancel out, and 1 yx and 1 yx is going to cancel out. So I'm going to obtain xy plus yz plus zx. So this gives me x minus y, y minus z, z minus x into xy plus yz plus zx. Here a little bit of arrangement has been done. I've taken minus 1 as common from this bracket y minus x to obtain x minus y, and multiplied in this bracket z minus y to obtain y minus z, and this z minus x as it is. So I have to prove that the determinant is equal to x minus y, y minus z, z minus x into xy plus yz plus zx. So this has been proved it as equal to the same. So hence the question is proved.